So we are considering differential work integral, and this differential work integral considers a particular mass element and its change of pressure and volume during oscillation or during the perturbation. And usually then our mass elements, this is a particular mass element within our star which we follow in the course of time. So once we have a pulsation, then usually this is a closed contour in the PV diagram. So the pressure and volume starts at some point and it returns again to the original point once we have a strictly periodic motion of our star or the mass element within the star. And we convinced ourselves that the work done by this element or consumed by this element is simply the integral over the path in the PV diagram. So this is the integral over one cycle, integral P dV over one cycle of pulsation. So this is one mass element which is considered here, and the differential work integral denoted by V dash then tells you whether at this position or by this mass element within a star, energy is either produced, meaning energy is transferred from heat to mechanical energy, or vice versa, which energy is dissipated from the mechanical energy and goes into heat. These are the two ways. Okay, so we already discussed this. So during the pulsation, the kinetic energy or the mechanical energy is increased or dissipated per mass at the rate. We can now rewrite this PdV work in terms of the change of the mechanical energy with time of the mass element. This is given by the change of pressure or the pressure, the Lagrangian pressure perturbation times the time derivative of the Lagrangian volume, or alternatively the Lagrangian density perturbation. Well, a suitable average over one, of course we have to average over one circle because locally this does not have a meaning, so over one circle averaged or taking a suitable ensemble average over the pulsation of pulsating equivalent pulsating configuration, then we end up with the following form for the differential work integral. It can be expressed in terms of the eigenfunctions, so to say, in terms of some components of the eigenfunction, namely the eigenfunction component Lagrangian relative Lagrangian pressure perturbation and relative Lagrangian temperature perturbation. And then, if you perform the analysis, then the differential work integral, that means the energy dissipated or generated per integration interval per mass of the mass element, is then proportional to the imaginary part of the product of the pressure perturbation times the complex conjugate of the temperature perturbation. Okay, so if W dash, the differential work integral, is bigger than zero, then mechanical energy is provided. That means the perturbation or the oscillation is excited, or in other words, it is a driving region. It drives the pulsation. If the differential work integral is smaller than zero, then mechanical energy is dissipated. This is a damping region. This leads to a damping of the oscillation. This, of course, is the normal case. Usually, the energy is dissipated and energy is taken out of the pulsation. That means the mode or the oscillation is damped and its amplitude decreases, and ultimately you end up with the hydrostatic model you have started from. Okay, this is per mass or per integration interval. We have used log P naught as the independent variable. So this is the energy per interval in log P naught. And once we would like to know whether we have an excited or a damped mode, then we have to sum up all the driving, all the mass elements, and summing up over W dash of the driving regions and the damping regions, and then we get either a positive value of this integral. This means the driving regions overcome the damping regions, and we have on total we have a mode which is excited, and if the integral is negative, then the mode will be damped. This is the normal case. So we have instability once the integral over W dash is bigger than 0, and stability or damped mode once this integral is smaller than 0. In that way, we may identify within the star those regions which are driving and those regions which are damping. Okay, well, this gives you the position where a mode is excited or damped, but it does not provide any explanation or mechanism for the instability. The second step would then be, once we have a driving region, what is special with the other quantities appearing in our equations? For instance, how does the derivative of the energy generation rate behave in this region, or how do the derivatives of the opacity behave in that region? And then to correlate the driving regions with other quantities like derivatives of opacity and energy generation rate. So keep in mind, this differential work integral only tells you where a mode is excited, but not what the mode, what is the mechanism that excites the mode. Okay, so W dash might be a useful tool to identify damping and driving regions within a star, and it can give you hints on the instability mechanism. It does not give you the instability mechanism, or it does not tell you what is the instability mechanism which is present. Keep in mind also, this analysis is based on the assumption that our star or the excitation of our pulsations are done by a Carnot-type process. That means the instability is caused by transfer of heat energy into mechanical energy. So let's consider two examples. The first one is a 0H main sequence star of 87 solar masses, and we consider the first overtone, which has a frequency of 2.43 in our normalization, and which is unstable with a growth rate of minus 1.9 times 10 to minus 3. And for the second model, we consider a 120 solar mass 0H main sequence star, which has a frequency of 1.3 and which has a very low value of sigma I of minus 1 times to 10 to minus 6. So this is a very weakly unstable fundamental mode in the 0H main sequence star with 120 solar masses. So let's go to the 87 solar mass star. Here as a function of log P, we have the W dash, and we see here there is a domain where W dash is negative, so this is a driving region, and this here is this is a damping region, and this is a driving region. And if we take the integral over this function, then the integral is positive. So this area under the curve, this positive, the area under the positive value of the curve is bigger than the negative one. So this corresponds to an excited, unstable mode. Now, once we relate this domain where driving occurs with the properties, the other properties of the stars, we observe that exactly in this domain or in this region, we have positive values of the derivative of kappa with respect to temperature. So it seems that this driving region is caused by positive values of the derivative of the opacity with respect to temperature. Okay, now let's go to the 120 solar mass star. Well, again, we have a very similar behavior here in the outer part of the star, in the close to the surface of the star. Again, as a function of log p, we have the differential work integral. Again, we have a negative part, this is the damping region, and we have a positive part where the differential work integral is positive. And there are some negative parts here as well. So this leads to damping, and the integral over the entire differential work integral is again positive, but it's weakly positive only. And well, there is a second part very close or at the center where the differential work integral is positive. And once we look what is going on there, then we find that the derivative of the energy generation with respect to temperature is positive there. So this is the positive value of kappa T is associated with the driving region, and the positive value of epsilon T is associated with the second driving region. So this is called the Kappa this is the Kappa mechanism which is responsible for driving, and this is the epsilon mechanism which is responsible for driving. Well, the weakness of this instability is mainly caused by the weakness of the epsilon mechanism, and what you see here at the same time where the epsilon mechanism is present, we also have the Kappa mechanism present. So there are two mechanisms which compete with each other, and it's always the Kappa mechanism is always present, even if the epsilon mechanism also in those cases where epsilon mechanism is present. So they are competitive effects concerning the driving. Okay, so what we saw here, this is the result. Well, damping and dissipation is the normal effect, and driving is found once either kappa T is bigger than 0, then this is called the Kappa mechanism, and if epsilon T is bigger than 0, this is the epsilon mechanism. Both modes are affected by the Kappa mechanism, as you saw. Both modes show driving in those regions where kappa T is bigger than 0, but only the fundamental mode showed a driving region associated with positive epsilon T. Well, once the epsilon mechanism is working, it is extremely weak. So the growth rates obtained from the epsilon mechanism are very small. This is not surprising because the epsilon mechanism should work on the nuclear timescale. Nuclear timescale is much bigger than the dynamical timescale. So the growth timescale is usually, if it's caused by epsilon mechanism alone, then the growth timescale is proportional to the nuclear timescale. It is only found, this is a result which I just quote here, it's only found in the very vicinity of the 0H main sequence. If you go off the 0H main sequence, the epsilon mechanism will no longer work, and you need masses at least of 60 to 150 solar masses to see this epsilon mechanism. Moreover, it is opacity dependent. That means the opacity plays at least an equal role as the energy generation for having an instability. So the epsilon mechanism always competes with the kappa mechanism. So there is a competition with much stronger instabilities in general. So epsilon, keep in mind, epsilon mechanism is very weak. The time scale on which the epsilon mechanism operates is nuclear time scale. The growth time scales are very, very small. And it is restricted to the very vicinity of the 0H main sequence. Which means, if you compare it to the evolutionary timescale of the star will take the star the same time, or the time for the star to evolve off the main sequence or out of the epsilon instability domain is comparable or even shorter than the time it needs for the instability to grow by a factor of E. That means this epsilon instability, it is present. It is certainly correct to deal with the epsilon mechanism, but it is of academic interest only because the star will move out of the instability region before the instability can grow significantly. So actually, this was the first instability mechanism proposed by Eddington. He is right, of course, the effect exists, but it is not of interest for realistic stars because the timescales are simply too long for this instability to grow. Okay, so now we would like, of course, to have the next step a intuitive model for this epsilon and kappa mechanism, and it's already been addressed yesterday, partially by Professor Yadav. Let me just briefly comment on an intuitive model for this kappa and epsilon mechanism. Well, we have to start with, once we consider this mechanism, we have to start with a periodic motion or a periodic cycle within our star. So consider our star performs an adiabatic pulsation. So it's a strictly periodic motion. The amplitude stays constant and the star returns after one pulsation cycle. The star returns to its initial state. Okay. Well, all these Carnot-type heat engines require a cyclic motion, like a diesel engine or a fan, aircraft engine. All these engines, they need a cyclic motion to start with, and the cyclic motion here for the star might be considered to be the adiabatic pulsation of the star with constant amplitude. Well, what happens in the state of maximum? Well, we have a star which pulsates. We have compression and decompression of the star. So in the case of a radial pulsation, the star changes its volume and therefore it has a point of maximum compression. This means the highest density corresponds to maximum compression. And since it's an adiabatic pulsation, then also the pressure will have a maximum. What about the temperature? If you have adiabatic motion and you have compression and decompression, density changes in the first place, then pressure changes. What happens to the temperature in adiabatic motion? Temperature at the phase of maximum compression will be maximum. So you have a temperature change during adiabatic changes of state. So in the phase of maximum compression, we'll have a phase of maximum temperature. If then if you then insert or if you release additional energy in the phase of maximum compression, that means you put in energy for instance by igniting fuel in a diesel engine or in an aircraft engine at the phase of maximum compression, you insert or ignite some fuel, then you add up an additional amount of energy, you deposit an additional amount of energy at this phase. An additional amount of energy will give you an additional increase of temperature in excess of the adiabatic temperature increase, and this temperature increase, this additional temperature increase will then give you an additional pressure increase, which in addition to the adiabatic pressure restoring, will give you an additional restoring force from the additional pressure, which is caused by the ignition of fuel and so on. So this was the model which Eddington proposed in the initial phase, or in the once he studied stellar pulsation and the excitation of stellar pulsation, and that's what is done once we consider the epsilon mechanism. So if we have an additional energy release in the phase of maximum compression, caused, for instance, by adiabatic motion. If you have additional energy release, for instance, by nuclear processes, and these are the processes we had in mind, then we have an additional increase in temperature and pressure, and we have an additional restoring force over in excess of the adiabatic restoring force, and this means that then the amplitude will increase and we have an instability. What we need for that is that with increasing temperature, or with at the phase of maximum compression, we have an additional energy release. That means that the change of the energy production rate, the energy generation rate, epsilon, must be positive. Epsilon t must be positive. The dependence of the energy generation must be such that the energy generation increases with temperature. Then this diesel engine or turbofan engine mechanism will work. Okay, so this was the original description of epsilon mechanism by Eddington, and we saw, well, it seems to work. It is actually a mechanism which has to be discussed for stars, but it is only of academic interest because the timescales are too long for this instability to grow. Well, another mechanism which we have already seen is the Kappa mechanism. Well, this works in the following way. If the opacity increases with temperature, that means if in the phase of maximum compression and the phase of maximum temperature, the opacity is increased, kappa t is positive, then the material, the stellar material, reduces the transparency with respect to the transport of energy. Increased opacity means the transparency is reduced. That means that the radiation coming from the interior is damped up at such a zone and needs to be stored somewhere. So radiation comes from the interior. Opacity is increased in the phase of maximum compression, so it has to stay there. That means the heat has to be put or deposited in the corresponding mass element. So when this heat is to be stored, we have an increase in temperature and pressure, and then similar to the epsilon mechanism, we have an additional restoring force, and in addition to the adiabatic restoring force in that phase. Again, this leads to an amplitude increase and to an instability. So this is the intuitive model for the Kappa mechanism to work. We start with a cyclic motion, for instance, from an adiabatic pulsation, and then in the phase of maximum compression, we obtain an additional restoring force, which is caused by the deposit of additional energy, and this additional energy comes either from an increased nuclear energy generation or by damming up the radiation there, which then needs to be stored at the respective mass element. Okay, that's the intuitive model for Kappa mechanism and epsilon mechanism. Epsilon mechanism is of academic interest, and the mechanism which is responsible for all the classical pulsating stars is actually the Kappa mechanism, and it requires a positive derivative of kappa with respect to temperature. Okay. Well, again, to summarize. Epsilon mechanism only close to zero-age main sequence is very weak. Growth timescale competes with evolutionary timescale, and therefore it's only of academic interest. I should note here perhaps that epsilon mechanism has in former times been discussed always with the maximum mass a star can have, because people have considered the epsilon mechanism along the main sequence, and they found these epsilon mechanism sets in at masses around, well, it depends on the author and it depends on the opacities people have used, of the order of 100 solar masses. And this was thought that the epsilon mechanism, this instability, is responsible for setting an upper limit to the mass. This is, of course, no longer true, because the star has evolved already out of the instability domain before the instability is able to grow by a factor of E. So what people have ignored is the weakness of this instability, probably because they couldn't calculate these small rates, and they haven't considered the fact that the epsilon mechanism is only restricted to the very vicinity of the zero-age main sequence. But still today, from time to time, you find in the literature people are talking about the epsilon mechanism and its relevance to the stability of star. So be careful. The epsilon mechanism does exist, but it does not have any relevance for realistic stellar models. Okay, the Kappa mechanism is working for kappa T bigger than zero. In general, the derivative of kappa with respect to temperature is negative, so this is the exemption. Kappa T bigger than zero occurs only at certain stages or at certain domains of the temperature range. And it is responsible for the majority, for the excitation of pulsation of the majority of stars. So where does this, where do regions or where do temperature ranges occur where kappa T is bigger than zero? Well, let's have a look. This typically occurs, we have already seen this diagram. This is a cut through the temperature density plane. It plots, or what is given is kappa, the opacity, as a function of log temperature for some constant density. And what you see here, usually the opacity decreases with temperature, but there are, here it decreases, but there are three domains in temperature where the opacity increases with temperature. This is here, here, and there. And what causes these three maxima in opacity? These are ionization processes and the contribution of heavy elements. So this is hydrogen and first helium ionization. This is second helium ionization, and this is the contribution of the heavy elements. So these three slopes, these three positive slopes, may give rise to a pulsation, to a class of pulsating star, and actually this is true. This is the branch which is responsible for the Cepheids, for the delta Cepheids, and this branch, for instance, is responsible for the pulsation of beta Cepheid stars. Okay, so what we have, there are three domains where kappa T is bigger than zero: hydrogen, helium, helium-2 ionization, and the contribution of metals. And these three processes give rise to the excitation of pulsations of various stars. Here, maybe I can get this a little bit smaller. Can you reduce the size? Thanks. That should be okay. Okay. This is an HR diagram where the different classes of stars have been inserted. logarithm of luminosity against the logarithm of temperature, high temperature on the left-hand side. The dashed line is the main sequence, and the hatched regions are the domains where the various variables are found. The most prominent variables are the delta Cepheids. They are found in a strip indicated by dashed lines here. This strip also contains the RR Lyrae star, the delta Scuti stars, and if you extend this strip to the white dwarf regime, then also there are some white dwarfs found which suffer from instability caused by the Kappa mechanism, and this is the Kappa mechanism which is due to the helium, the second helium ionization. So you can directly relate the positive Kappa T values in the opacity diagram with the excitation of a certain class or a group of certain class of pulsating stars. Then you have at higher temperatures, of course, then also at higher effective temperature, you have the beta Cepheid star. They are they are excited by the heavy element opacity bump, by the positive kappa T related to that maximum of the entropy of the opacity, and the slowly pulsating B stars belong to that group. Also, there are some stars which suffer from the kappa instability due to heavy elements. These stars on the right-hand side, they may be, it's not very clear, they are also affected by convection. They're the first opacity maximum due to hydrogen-helium ionization plays a role. So you clearly can see this is Kappa mechanism by helium-1, by a second helium ionization, possibly hydrogen ionization, and these stars by the heavy element opacity bump. Actually, I already told you the story about beta Cepheid stars. Before people have calculated correctly the heavy element opacities, there was no reason or there was no model or explanation for the pulsation of beta Cepheid stars, and people have invented exotic models including rotation, magnetic fields, and so on to get these beta Cepheid stars pulsating. And once they came up with the correct opacities, no problem was left. The beta Cepheid stars pulsate because there is an additional opacity bump due to the contribution of heavy elements. So all these stars have been found or have been explained. Their pulsation has been explained once the opacity were calculated correctly in the mid-90s of last century. Okay. Well, finally, we use usually the period. Cepheids are used for distance determination, and for the distance determination, we make use of the period luminosity relation. So, if you know the period of a pulsating Cepheid, you can derive, or you have you know its absolute magnitude or its luminosity, and of course we would like to know how this period luminosity relation may be justified. What we observe here is that the excitation of pulsations in the instability regions for Cepheids is a narrow strip in the HR diagram. So this narrow strip might be parametrized or might be described by a relation between effective temperature and luminosity. So the conditions, the proper conditions for the excitation of Cepheids by the Kappa mechanism due to the second helium ionization may be described in terms of a luminosity temperature relation of the strip, the instability strip in the HR diagram. Okay, so to somehow motivate the period luminosity relation, we start off with considering or with stating that the instability strip is given by a temperature luminosity relation. Well, Stefan Boltzmann's law is of course valid in the entire HR diagram. Once the temperature is only a function of luminosity, then according to Stefan Boltzmann's law, the radius will be a function of luminosity only as well. Now we know that all stars have to satisfy the mass luminosity relation. So if this means that the mass is also only a function of luminosity, then we know then the density is maybe approximated by mass over radius cubed. And if mass is a function of luminosity only and radius is a function of luminosity only, then the density is a function of luminosity only as a consequence. Now we know there is a famous period density relation. That means the period of the star goes with rho to -2. There's no secret behind it. It's simply the dynamical timescale which is responsible or which governs the pulsation of the star. So if the density is only a function of luminosity, then the period will be a function of the luminosity as well. So this is a motivation how the period luminosity relation may be justified, or how we get this period luminosity relation. And this period luminosity relation is one of the most important tools to determine distances in astrophysics. Now we have arrived with the Kappa mechanism as the mechanism which is responsible for exciting the pulsation, and then inserting all the physics or all the formulae or all the relations we know from stellar physics or instability strip. We have made use of Stefan Boltzmann's law, mass luminosity relation, then period density relation, and we finally end up with a period luminosity relation which can be used to determine distances. Okay, now we've considered the standard mechanism for exciting stellar pulsations. Well, this is mainly the range or the regime with, I don't need to expand it. This is the range or the regime of stars which are moderately luminous. And what we are doing now, we will extend this diagram towards high luminosities, or in other words, to high luminosity to mass ratio. So we will go to the upper end of this diagram. These are the classical pulsators driven by Kappa mechanism here, and we will go to stars which are much more luminous and which have much higher luminosity to mass ratios in terms of solar values. So luminosity to mass ratio is given usually in terms or in units of the solar luminosity and the solar mass. So luminosity to mass ratio means that the luminosity to mass ratio of 10⁴ means that luminosity in units of solar luminosity divided by mass in units of solar luminosity is of the order of 10⁴, or any other value given. Okay, so we go to stars and consider pulsating or unstable stars in the upper part of this HR diagram. Okay, this will be done in the next file, and this file is called, its title is Strange Modes. So first of all, where are these strange modes found? What are the stars we are considering now? I promised you these are luminous stars, or in other words, not luminous stars, which does not mean these stars are massive, but their luminosity to mass ratio is high. The first example for the occurrence of these strange modes are the so-called hydrogen deficient carbon stars, or extreme helium stars. They are also called prominent example is the star R Coronae Borealis. So this is the prototype of hydrogen deficient carbon stars. The chemical composition of these stars is almost zero hydrogen. They almost consist completely of helium, carbon and oxygen. So it is hydrogen deficient means there is almost no hydrogen. Well, when one can represent models for these stars by following the evolution of a generalized main sequence. Generalized main sequence means we are constructing now main sequence models using an initial composition which does not contain hydrogen but which contains only helium. That means this main sequence is defined by the ignition of helium rather than of hydrogen. So it's a helium main sequence which we consider, and we start off the evolution of these stars by requiring complete or essentially helium content and a little bit of carbon. So the evolution starts off the helium main sequence, and we follow the evolution then of this so-called helium star. How does it look like? Well, sorry for the quality of this picture. It's pretty old. So here is the HR diagram for the evolutionary track of this guy. So the effective temperature ranges from 4.8 to 3.4, and the luminosity. This is the evolutionary path of this star. We see here the helium main sequence phase, and then a helium shell burning phase, and in this phase the luminosity becomes very high, and the models we consider for stability are the models between these two temperatures. You see the luminosity here is around 10 to 4, and the mass of this object is 0.9 solar mass. So this guy has a pretty high luminosity to mass ratio. These are the models which are considered in the range of, say, 4.3 to 3.6 around log TF values. Okay. What do we find here? Well, these are the models which we consider for stability, and what we find if we perform now a stability analysis and look for the modal diagram which we determine, then we find the following result. Okay, here maybe we can get a little bit smaller here. So as if perhaps a little, okay, thanks. So along the evolutionary track, so we take models along the evolutionary track, and they are labeled with the effective temperature between 3.6 and 4.6 here. And sigma r, the real part of our eigenfrequency, is plotted as a function of model or of model parameter, or here in terms of the effective temperature. What we observe here is, well, there is a sequence of modes which is more or less equally spaced and which does not depend very much on the model. These are the modes which we expect for any ordinary acoustic resonator. Like for an organ pipe, we would expect an equally spaced spectrum of eigenfrequencies, and these should not depend very much on the model parameter, because we have accounted for by our normalization for the period density relation. So the modes should in any case follow the period density relation. So this relation is also already accounted for, and because we have accounted for the period density relation, we should have a weak dependence on stellar parameters of these modes. So these modes are expected, but what is not expected is some modes which have a strong dependence on stellar parameters and which cross these modes. So here is a mode denoted with Roman A. There is one with Roman 2, there is a mode with Roman 5, which have a strong dependence on stellar parameter and which cross the spectrum of the other modes, the normal modes which we expect in any case. So what about the imaginary part of these guys? Well, associated with mode 1 here are in fact instabilities, and that makes these modes very exciting. Not exciting the star, but exciting for us. So the mode 1 is the imaginary part of mode 1 is negative, so this corresponds to instabilities, and these instabilities are in fact not weak, but they are of the order of the dynamical timescale. So they range up to minus 0.25 here. So we would consider this as a dynamical instability. So it grows on very fast, on very short timescale, and there is an additional mode, the mode 5, which is also a member of this strange, or of these additional modes, which has an even higher growth rate of minus 1.5. So, well, the exciting thing about this is there are additional modes which we haven't expected, and moreover, these modes are unstable and leads to an excitation, or may lead to an excitation of modes. Maybe you see here that this is not a monotonic line here, but this line has some maxima. So it seems there are some maxima hidden behind in the growth rate, hidden behind this mode denoted with Roman 1. Okay, so let's go back. Well, the observation or the result is there seem to be additional modes, and because nobody knew what to do with these modes, because they are not expected, they have been called strange modes. There's nothing behind, no secret behind it. Strange modes are additional modes. Well, for sometimes people have tried to define it in terms of physical classifications. This has failed. Some people have said the strange modes are secular mode. That means they are thermal modes. But because some of them are also strongly damped. But here we have the example that these strange modes, these additional modes, are actually excited or are unstable. So there is up to now no clear definition, no mathematically strict definition of the term strange modes. I would like to address as strange mode any mode which behaves unexpectedly. So anything that is unexpected or is not covered by the normal behavior of an ordinary acoustic resonator like an organ pipe, anything that deviates from an organ type like spectrum is addressed as a strange mode. Okay, so well, the second part, strange modes are often, not always, associated with strong instabilities, and the growth rates are in a dynamical regime. Sigma I is of the order of minus 0.2 or even smaller. The question then, of course, is, are these modes, and this for a long time people have thought they are of thermal origin. Actually, this is not true. They are of mechanical origin. So we'll come to this point later on, and we'll see that they are not of thermal origin, but they are of mechanical origin. Okay, so hereafter strange modes are denoted, or we call strange mode any additional modes in addition to what we would be expected from an ordinary acoustic or resonator like an organ pipe. What we observe once we compare these stars, these extreme helium stars, with normal stars, with normal I would consider or denote a Cepheid, well, is that the ratio of thermal to dynamical timescale is significantly smaller than for normal stars. This is associated with the fact that the luminosity to mass ratio here is bigger than 10 to 3, and in some cases it's also already of the order of 10 to 4. So let's go to the run of the we have already seen this diagram. Here we compare the ratio of thermal to dynamical timescale as a function of position within a star for a normal star, a Cepheid, and a hydrogen-deficient carbon star. You see this ratio increases once we go to the center, so close to the center, all the pulsations behave adiabatically, and close to the surface, this is of order unity. There, non-adiabatic effects come into play. Well, for the Cepheid, this domain where the thermal timescale is of order unity or even less is much smaller than for the hydrogen-deficient carbon star. For the hydrogen-deficient carbon star, this ratio is smaller, and the domain where this ratio is smaller than unity is also bigger. So when property of this hydrogen-deficient carbon star is that the ratio of thermal to dynamical timescale is much significantly smaller than for normal stars like Cepheids. That means, well, concerning the comparison of the adiabatic approximation and the full problem, well, for these stars we expect significant deviations once we do an adiabatic analysis, or if we compare an adiabatic analysis with the full non-adiabatic analysis, because these stars seem to behave or seem to deviate from adiabatic behavior, because the domain where the thermal timescale is small is much bigger. So we expect adiabatic and non-adiabatic analysis to differ from each other, and well, to provide significantly different results. The adiabatic approximation is expected not to be satisfied, as for instance in the Sun, where adiabatic approximation is a pretty well-defined and well-satisfied approximation. What goes along with the small ratio of the thermal to the dynamical timescale is that the contribution of gas pressure to total pressure is usually smaller than for the ordinary stars. If we write the pressure as a sum of gas pressure and radiation pressure, then the ratio of gas pressure, the contribution of gas pressure to total pressure, is significantly smaller than one, which goes along with small thermal timescales. So there are two properties which we need to mention, or which are special with these stars: small thermal timescales and small contribution of gas pressure, or in other words, dominant radiation pressure. Radiation pressure is important for these stars. In the same time, the thermal timescale are small compared to the dynamical timescale. Okay, so this is one example for strange modes, for the appearance of strange mode. Well, you already know this diagram. I have plotted here the ratio of thermal to dynamical timescale for two massive stars, and we see the same behavior. Large masses correspond to high thermal timescales, and once we reduce the mass, the range where the thermal timescale is small is bigger for the low mass stars compared to the 60 solar mass star, where the domain where thermal timescale is small are only the outermost 10%, whereas for the 24 solar mass object it's almost half the radius. Well, and for this example I've already brought the ratio of gas pressure to total pressure, and you see for the 60 solar mass star the contribution of gas pressure never falls below 10%, whereas for the 24 solar mass star associated with a small thermal timescale, the fraction of gas pressure in the star can become much less than 0.1. So the small thermal timescales are often associated with small contribution of gas pressure, or alternatively with dominant radiation pressure. Now, well, once the strange modes in hydrogen-deficient carbon stars have been identified, a short time after that, Wolf-Rayet stars have been considered, and they are found to be the most extreme example for these additional or strange modes. Well, also the Wolf-Rayet stars are characterized by the same properties as the hydrogen-deficient carbon stars, thermal timescale divided by, or the ratio of thermal to dynamical timescale is much smaller than unity, and the contribution of gas pressure to total pressure is also smaller than unity for a large fraction of the envelope. Well, the standard representation of Wolf-Rayet stars are again generalized generalized main sequence models. They are helium 0H main sequence models. So if I will show a sequence of models, then this is a helium main sequence. These are helium main sequence models where the lowest luminosities are corresponding to the low masses, and the highest luminosity correspond to high masses. So this is a generalized main sequence. So putting a star with no hydrogen and essentially helium, carbon, and oxygen on the position where helium is just ignited at the center. This defines the helium 0H main sequence, and the helium 0H main sequence has as a parameter the mass. So log L against log TF, and defining the position where helium is starting to burn, then this gives a sequence in mass, and this is M. Here on the bottom of this sequence, M is small, and here is M is high. So they are represented by helium 0H main sequence models. Okay, now let's have a look what the stability analysis with respect to radial perturbations, non-adiabatic stability analysis with respect to radial perturbations, what the result is. Just take the upper part. Well, here, this is the bottom part of this is now the real part of the frequencies as a function of mass along the main sequence. This is the bottom of the main sequence, and this is the top of the main sequence, ranging from 3 to 18 solar masses. Okay, so the real parts of the frequencies show a type of spectrum which we expect. We have a set of more or less equally spaced modes or frequencies with weak dependence on the stellar parameters, with weak dependence on mass. But superimposed on these modes, superimposed on this normal spectrum, is an entire set of modes whose dependence on the parameters on mass, on the parameters of the star here, the mass, is much stronger, and their frequency decreases with mass, thus crossing the spectrum of the ordinary mode. So we have two sets of modes here, one of which we expect, and the other one which stronger dependence on stellar parameters, which cross these modes, and which is there in addition to the ordinary spectrum. So we call them unexpected modes. These are strange modes. Once these modes are unstable, they have been denoted in this diagram with thick dots. The tiny dots correspond to damped modes, to stable modes. So if we consider now the imaginary part belonging to that, well, what we observe then is the following. Well, we have lots of modes which have positive values of sigma I. These are stable, and these are essentially the normal modes. All the normal modes are stable and have positive values of sigma I. But once these strange modes enter the diagram, then they seem to come in a almost complex conjugate pair. So there is one strongly unstable mode, so one strongly mode in the pair having growth rates or having sigma I values of -2, and at the same time, once this appears, also a mode with the corresponding damping appears. Well, these modes actually have almost the same real part, the same frequency. It is not that obvious because below or close to these thick dots, which denote the unstable modes, there is a tiny dot which belongs to the mode with the almost complex conjugate value of sigma I. So these actually, below these lines, or these lines denote two modes, one of which is unstable and one of which has a high damping rate, and they appear in the imaginary parts as complex conjugate pairs. So the result is these are the ordinary damped modes, and these are the modes which appear in this diagram, one having a negative, one having a positive value of the imaginary part, and they are almost not perfectly, but they are almost complex conjugate symmetric. Well, perhaps you can see in this diagram another point. Well, it seems, well, we would call this, for instance, we would call these ordinary modes. But what happens, what seems to happen is that these modes seem to merge, and then they generate by merging this pair of complex conjugate modes. That seems to happen here as well. There are two modes which seem to merge to form the strange mode, and then the strange mode goes depends stronger on the stellar parameters and goes that way. So at a few places it seems that these strange modes seem to emerge from the ordinary spectrum. Okay, so this is what we find once we consider helium-0H main sequence models for to represent models of Wolf-Rayet stars. Okay. Well, I'm supposed to stop here. Then we will continue at this point. Thanks.